In the first chapter, both the exponential function with the base e and the continuous compound interest were introduced informally. Now, with an understanding of limit concepts, we can give precise definition of e and continuous compound interest. The constant e. The irrational number e is a particularly suitable base for both exponential and the logarithmic function. The reason, actually you know, which is noted by ln x, the reason for choosing this number as a base will become clear as we develop differentiation formula for the exponential function e to power x and the natural logarithmic function ln x. In precalculus treatments, the number e is defined informally as the irrational number that can be approximated by the expression 1 plus 1 over n to power n for n sufficiently large. Now we use the limit concept to formally define e as either of the following two limits. So definition: e is limit when n goes infinity 1 plus 1 over n to power n, or equivalently e equals to number limit when x goes, or let's say s according to your textbook, s goes infinity 1 plus s to power 1 over s. Here the both limits are the same clearly, equals approximately 2.718281 blah 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 blah. Okay. I will not give the proof of to these limits. Now we can see how e appears quite naturally in the important application of compound interest. Okay, so continuous compound interest. Let us start with the simple interest. How on to compound interest and then proceed on to continuous compound interest. In the lectures, I tried to explain the situation to you. Okay, so in your textbook now you can find this explanation. On one hand, if a principal P is borrowed at an annual rate R, then after 3 years at simple interest, the borrower will owe the lender an amount A given by principal plus principal times the annual rate. This rate should be a decimal place number times t, or p times 1 plus rt. This is simple interest formula. If r is the interest rate written as a decimal, then 100 times r percentage is the rate is percent. Okay, for example, if r is 0.12, that means r is 12 percentage. Okay, in the lecture time we have already discussed this situation. So the expressions 0.12 and the 12% are equivalent. Okay, so these are the equivalent notation. Unless stated otherwise, all formulas in the book use are in decimal form. Okay, as always I said, we use this decimal form. On the other hand, if interest is compounded m times a year, then the borrower will owe the lender an amount A given by the following formula: A equals P times 1 plus R over m to power m times T. This is a compounded interest formula. Where R over m is the interest rate per compounding period and m times T is the number of the compounded period. Suppose that P, R and T in this equation are held fixed and m is increased. Okay, so in this case, will the amount A increase without bound, or will it tend to approach some limiting R? In the lectures we discussed and I said that this is limited. So let us perform a calculator experiment before we attack the general limit problem. If P is $100, R is 0.0, so this is 6%, and T is 2 years. Then A equals, by using the compound interest formula, 100 times 1 plus 0.06 over m times 2m. So for the sum values of the m, we compute the values A. Okay, let's make our table left side. Compounding period or frequency, M, and the A, future money. So if this is annually, M is 1, and the future money, by using this formula you can calculate this price. If this is semi-annually, I performed the same calculation in the lecture, most of you will remember. That is that part, sorry, comma, and quarterly you can calculate. As you see, the numbers, the values, future values are not big, but it is increasing, you can observe. And monthly, M is 12 and 71, and weekly M is 52, $112.74. Maybe we can write the 0 here. And daily, M is 365, and our future value is 112.74 cents. Again, after the comma change. Okay, maybe we should write this is 74.19, sorry, 86, 71.60, 93.09, 0. So by looking at your textbook, I'm writing these results. Okay, you can verify. And the last one is, for example, hourly. During the year, there are 7,670 hours. So this is 112.74.96. So keeping P and R and the T fixed in the equation, we pull P outside the limit using a property of the limit. Okay, so we can say that limit when m goes to infinity, P times 1 plus R over m to power m times T equals, P is constant, by the properties of the limit we can write outside of the limit, 1 plus R over m to power m times T. The limit properties we show that, okay, by making some substitution we can change and you can obtain the some familiar form. Let S equals R over M, so M times T equals R times T over S. In this case, when M goes infinity, S goes to 0. Yes. So this limit equals P times limit when S goes to 0, 1 plus S to power R times T over S. As a result, we obtain the following limit: 1 plus S to power 1 over S. You are familiar to this limit and power R of T. So this limit goes to E. So this is E to power R times T. So the resulting formula is called a continuous complement interest formula, okay? This is continuous compound interest formula. This is a widely used formula in the business and the economy.